Hello everyone, my name is Apurv and I'm here with a very interesting physics problem. You can pause the problem and try the problem. You can pause the video and try the problem, and I hope you appreciate my handwriting. I'll explain the problem. There are 3 blocks here and all of them are elastic. What they mean by elastic is that if at all they collide, the collision is going to be elastic. Now these 2 blocks in particular are at rest. They're connected with are at rest initially. They're connected with a spring constant K, and the natural length of the spring is going to be L here in the question. Now initially the spring is in its natural length, therefore it exerts no force on these 2 blocks, and therefore initially they are at rest. The spring constant of the spring is K. The surface is entirely smooth, and therefore this block, if it is given a velocity v, which it is given, it should sustain that velocity. Okay, and it is given a velocity v, it goes here, travels here and collides with this block, and obviously they must form elastic collision, as the question says. All of them are elastic, so it collides here and gives it a velocity v, and both of them are of the same mass. Therefore this stops after collision and this is given a velocity v. At the very instant of collision, this is given a velocity v, and at the very instant of collision there is no extension or compression in the spring, this, and therefore if there is no compression or no extension, it should not apply any forces on these two, right? So at the very instant of collision, this is given a velocity v, but this is still at rest. That is a point to be noted. We must prove that the blocks connected by the spring always move in the same direction. Now what I said is, after this is given a velocity v, it collides here elastically. It stops because it stops, and this is given a velocity v, and it happens because this collision is elastic and both of them are of the same mass. Now first let us consider the momentum. So initially I'm considering the momentum for this system. And why can I conserve the momentum? Why is the momentum conserved? Is because this spring, the force due to the spring, is internal to the system, so we can do that. So in the initial momentum of the system is only the momentum of this block. Why? Because what I said was a point to be noted, is that at the moment of collision, this is given a velocity v. There is no extension in this or no compression in this, and therefore because there is no compression, this cannot move. Okay, this will only move if there is compression in this. So initially the momentum of the system is mv, is equal to, let us call this block 1 and let us call this block 2. After the collision, at any instant, let's say the velocity of 1 is going to be u1 and that of u2 at any instant after the collision, any instant is u2. For 1 it is u1, for 2 it is u2, and at this very instant, when the velocities of both the blocks are u1 and u2 respectively, for 1 and 2 respectively, the extension of the spring, let's say, is x. Now these are the definitions that I have assumed here, some variables. Now to conserve momentum, the initial momentum is mv, finally it is going to be mu1 and then mu2. Okay, from here if you cancel all the m's, you get v equals u1 plus u2, and this is a very important equation you got here, call that 1. Now 2 is the second thing that I'm going to do is conserve the energy. Why? Because there is no friction here, we can conserve the energy, the mechanical energy. There is no friction, and let's do it. So initially even if there was friction, could have done something, but there's no friction, it's good. So half mv square, the initial energy of the system. Then afterwards it becomes, at any instant of the collision, it becomes half mu1 square for block 1, half mu2 square for block 2, and the spring also is compressed, so, or extended, whatever it may be, we that doesn't matter. The extension when the velocities of the blocks are u1 and u2 are, like I said, is x. The extension when velocities of 1 and 2 are respectively u1 and 2, the extension is x. So the energy in the spring is going to be this x, like I defined. Now you can cut all the halves, and v square is going to be u1 square plus u2 square. This is a straightforward simplification. You can m here, and so here v square is going to be, now this u1 square, I can complete a square here, okay, and this expression is equal to this. Okay, this is straightforward. You expand this, you get u1 square plus u2 square plus 2u1. You already have I wrote minus 2u and u2 here. Both of them get cancelled, you get the same thing. So this thing is this thing, kx square by m. Now this u1 plus u2 is, like I said, is v. So this is v square. So this entire thing gets cancelled with this. Okay, so we have 2u1 u2 equals kx square by m, or u1 u2 is equal to kx square by 2m. So the product of velocities of the both the blocks, this one and this one, 1 and 2, at any instant after the collision is going to be their product is going to be kx square by 2m. Okay, now notice that this k is always greater than 0. It is positive. M is also the same, always greater than 0. It's positive. 2 is a constant, greater than 0. Now this x square after the collision is definitely non-zero. So this, why at the instant of collision there is no extension in this. There is no extension in this. This only this has velocity v, and this has velocity v at the instant of collision, right? And therefore we had said that the initial momentum of the system is mv, not mv plus something that this might have possessed, because at the instant of collision this has no velocity because there is no extension. After the collision, this might get compressed and this will have a velocity. So what I concluded is after the collision at any instant, x is non-zero. Therefore this entire expression is greater than 0. All of them are positive and non-zero, so it is greater than 0 and not greater than equal to 0, greater than 0. So u1 u2 is greater than 0 because this is greater than 0, this is equal to this has to be greater than 0. Now because u1 u2 is greater than 0, because u1 and u2, the product has to be greater than 0, both u1 and u2 must have the same sign, which implies they move in the same direction, right? So we've proved that the blocks connected by the spring always move in the same direction. These two connected by the spring. We conserved momentum for this system, box system, and energy for this box system again. Okay, and then solved it, did some manipulations, and then we could prove this u1 u2 is greater than 0. That's all we had to do. Now one more thing, v got to be equal to u1 and u2. This is not a part of the problem, something else. u1 and u2 is greater than 0. Okay, but v is equal to u1 plus u2. V is a constant because that's the velocity this mass initially gets, right? It's a constant for a given situation, and this u1 and u2 are not constant, but their product they must have the same sign. So using these two facts that u1 and u2 must have the same sign and v is a constant, we can conclude that u1 and u2 must have the same sign as that of v. Right, that means if v is like this, both of them, u1 and u2, must also be like this. Now suppose this block was not here but in at this place, and it was given a velocity v like this. So this two block would have a velocity in this direction initially. So u1 and u2 would be like this. u1 and u2 would have the velocity, would have the direction as that of v. That's all. Thank you.